Welcome to The Explainer. Today, we're going to break down one of the most fundamental tools in all of math and physics, vectors. They're basically the language we use to describe anything that's got both a size and a direction, from the wind pushing on a sailboat to the path of a spaceship. But before we jump into all the numbers and arrows, let's start with a really simple question. Picture a game of tug of war. You've got two teams, they're both pulling their hearts out, but the rope isn't moving an inch. Why not? They're both pulling with a lot of force, so what's going on? Well, the secret lies in this idea of a vector. See, force is a vector. It's not just about how hard you pull, it's also about which way you're pulling. That's a vector in a nutshell. It's any quantity that has both of those things, a magnitude, which is just its size, and a specific direction. Okay, so here's our game plan. We're going to start with the absolute basics. Then we'll get into how to write and visualize vectors. After that, we'll see how to combine them. And finally, we'll put it all together and solve some classic problems. Let's do it. All right, first up, let's really get a handle on what a vector is. The easiest way to think about it is just as an arrow. Seriously, the length of that arrow tells you its magnitude, how big it is. And whichever way the arrow is pointing, well, that's its direction. And this is where it gets really cool, because this isn't just some abstract math concept. Vectors are everywhere. I mean, they're used to fly planes through tricky crosswinds, to figure out all the forces acting on a bridge to keep it safe, and even to create the awesome graphics you see in video games. They're like the mathematical bridge between our ideas and the real world. Okay, so now we know what they are. But to actually do anything with them, we need to learn their language. We need a clear, consistent way to write them down. So check this out. This slide shows the two main ways we do it. On the left, you can see a vector that goes from a starting point, L, to an ending point, M. So we can just call it the vector LM. But on the right, you see a much simpler way. Just give the vector its own name, usually a single, bold, lowercase letter, like A or B. But let's be honest, these arrows are just floating in space. How do we make them actually useful? Well, we put them on a map, a coordinate system. This is the absolute key, because it lets us describe them with actual concrete numbers. So on a simple 2D map like you see here, any trip can be broken down into just two parts: how far you go sideways along the x-axis and how far you go up or down along the y-axis. We call these the components of the vector, and this idea is super powerful. And the way we write these components down is beautifully simple. It's called a column vector. The top number tells you the x movement, how far right or left, and the bottom number is the y movement, how far up or down. Easy as that. Of course, we don't live on a flat map, right? We live in a 3D world. And extending this idea is surprisingly easy. We just add a third axis, the z-axis. You can kind of picture it popping right out of the screen at you, at a right angle to both the x and y axes. And that, of course, leads us to a 3D column vector. We just add a third row for that z component. And just like that, we can describe the position or movement of literally anything in three-dimensional space. Pretty cool, huh? So now we can describe any single journey or force, but the real world is almost always more complicated than that. You have multiple things happening at once, and this is where vectors really start to shine. We can combine them. Let's start with the most basic operation: adding them together. Vector addition is actually super intuitive. It's just like planning a trip. If you go from point A to point B, that's vector A, and then you go from B to C, that's vector B, then your total trip from where you started at A to where you ended up at C is just the sum of those two vectors, A plus B. We call that the resultant vector. And here's something that makes our lives so much easier. Just like with regular numbers, it doesn't matter what order you add vectors in. A plus B is the exact same thing as B plus A. This might seem simple, but this rule is a game changer because it means we can break down complex problems and solve them in whatever order is easiest. All right, theory's great, but let's get our hands dirty. It's time to apply what we've learned to a couple of problems. This is where you really see how these rules help us solve puzzles. So for our first challenge, we're going to play detective. We've got this four-sided shape, a quadrilateral named PQRS, and we're given some clues about its sides in the form of vectors. Our mission? Use vector algebra to figure out what kind of shape this thing actually is. Okay, let's look at the setup. We have this shape, PQRS. We're told the trip from P to Q is vector A, and the trip from P to S is vector B. We're also given one more critical piece of info. There's a point M, and it's the exact midpoint of the side RS. To figure out the shape, we need to compare its sides. Let's try to find an expression for the vector QR. The trick is, you can always find a path using vectors you already know. So to get from Q to R, we could go backwards from Q to P, then from P to S, and finally from S to R. Now, QP is just the opposite of PQ, so it's negative A. PS is just B. And using our other clues, we can figure out SR as well. Now, after you work through all the algebra, something really interesting pops out. We find that the vector QR simplifies down to 3 over 2 times B. Now let's put that side by side with the vector PS, which we already know is just B. And this reveals a massive rule in the world of vectors. If one vector is just a number, we call that a scalar, multiplied by another vector, it means they are parallel. Bam! They point in the exact same direction, even if they have different lengths. Since QR is just 1.5 times PS, those two sides have to be parallel. And what's a shape with one pair of parallel sides? It's a trapezium. Solved! Awesome. Now for our second challenge. This time, we're not just adding vectors. We're going to find the magnitude, the length, the size of the resulting vector. This is kind of like finding out the total strength when two different forces combine. So we're given these two vectors in 3D, P and Q, written out as column vectors. Our job is to find the magnitude of what you get when you add them together. First, we get the resultant vector. And this is the easy part. You just add the matching components. So 5 plus negative 1 is 4, 0 plus 8 is 8, and 8 plus negative 3 is 5. So our new vector is 4, 8, 5. Now, to find its actual length, we use our old friend Pythagoras' theorem, just, beefed up for 3D. You just square each component, add them all up, and then take the square root of the whole thing. When we plug in our numbers, that's 4 squared plus 8 squared plus 5 squared. We get 16 plus 64 plus 25. That all adds up to 105. So the final magnitude, the actual length of this combined vector, is a square root of 105. And that really brings us to the big picture here. This isn't just about passing an exam. This math is literally the blueprint for describing our physical world. The tension in power lines, the flight path of a space shuttle, the incredible forces holding up a skyscraper, even the little polygons that make up your favorite video game characters, all of it is modeled and calculated using vectors. So, we've unpacked the language of vectors. We've seen how these simple arrows give us a powerful way to talk about and work with complex forces and movements. They really are a blueprint for understanding the world in terms of both its size and its direction. So the only question left is, what will you build with it?